this set of Snap Circuits videos, we're looking at Project 466, the Meter Deflection 2, and ending with Project 488, the Open and Closed Door Indicator. So, with Project 466, there it is on the book, and here it is on the board. Now, this is actually a variation of a previous project, as the book says, because this references project number 358, which is just like this, except the diodes, the LEDs here, are in different polarities. So the way that the LEDs are configured here is the current is flowing in like this and then through the meter, as opposed to 358 where the current was coming out through the meter this way and then going through the LEDs. They would turn around. So this basically has the opposite effect of what Project 358 does. So with Project 358, the meter deflects to the right because our current is going that direction. But in this project, the current is going in the opposite direction. So our meter will actually deflect to the left below the 0 point. And in Project 358, the green LED lit first, and then the red when we turn the circuit off, because again, we're creating an alternating current with our transformer here. Of course, the opposite is going to happen here, where our red LED lights first, and then our green LED when we turn the circuit off by turning it on and off. So we'll see that. And of course, our 6-volt lamp here is just to both limit the current, but also illuminate when the transformer is energized. So turn on the switch, watch our red LED. See our red LED briefly came up. You may have seen our meter deflect. Turn the switch off, watch our green LED. And our green LED blipped there, because when we charge up the transformer, our red LED lights momentarily when the field in the transformer collapses, which gives us our other waveform for alternating current. Then it momentarily powers our green LED. And by turning the switch on and off really quick, we can make both LEDs turn on and off because we're creating an alternating current or AC signal. And as we're doing this, we can see that the meter is only deflecting below 0 because, again, the current is going in the reverse direction of what the meter expects. So because of that, it deflects to the left. So that is how project number 466 works. Now we're going to move on to projects 467 and 468, which is the automatic display. So here we are with project number 467 and 468, the automatic display. There it is in the book, and here it is on the board. So once again, we're making use of our 7-segment LED display. We're using our NPN transistor to drive the display here, which is being limited by a 100 ohm resistor, and then the base for NPN is being limited by our 100,000 ohm resistor, but we're also making use of our photoresistor here, which you can see I've got the 6-volt lamp sitting over it so that it reduces the amount of resistance there, because the way the circuit works is that we're taking current away from the base of the transistor there so that it cannot turn on, thereby turning on our 7-segment LED. So by keeping the resistance low on our photoresistor, the current just flows in a loop like this. None of it goes into our 7-segment LED display. Now, as I take our 6-volt lamp away from the photoresistor, the number 1 lights up, and if I cover the photoresistor entirely, well, it lights up nice and bright, because again now there's so much resistance on that photoresistor that the NPN transistor can pretty much fully turn on, and we get our number 1 showing on there. And again, as I let light into the photoresistor, it gets dimmer. You can bring the 6-volt lamp over to make it really bright. Well, now of course it goes completely out because we've lowered the resistance so much there. So that is how Project 467 works. Now Project 468 wants us to display the number 2 on it. So for that, we're going to connect A, B, G, E, and D. So we already got B there. We don't need C. We'll connect A. Get some more 2 snaps here. And let's see, G and E and D. And we'll start it like before. We'll put our 6-volt lamp over that, turn the circuit on. Again, nothing should happen because we got so much light going into our photoresistor. And as I take it away, number 2 begins to light. And once I cover up the photoresistor, it becomes nice and bright. And again, we got our number 2 showing on our 7-segment LED display. Let some light back in, it gets dimmer. Bring our 6-foot lamp over, and it goes completely out. So that is project number 468. So now we're going to move on to project 469. Actually, forgot there was more to this. So now we're going to connect, let's see, A, B, G, C, and D, because they want us to put number 3 up. So let's move this off to the side. So A, B, G needs C, and D. So leave that there. So bring the light back over. Let's turn the circuit on, nothing happens. Bring the light away. Number 3 begins to light. Cover it up, number 3 lights up nice and bright. Take away, it goes dim, and goes away. So that's 469, so 470 wants us to light the number 4. So we're going to connect points B, so take this away, G, C, and F. Put that there, take this away. Bring our light over. Turn on the circuit. And of course, number 4 is not shown there. Take it away, it starts to begin lighting dimly. Cover it up, it lights up nice and bright, the number 4. Take your hand away, it starts getting a little dim, bring our light back over, and it's completely out. Right. So that's 470, so project 471 wants us to put a number 5 up. So we're going to connect A, out of here, C, so we don't need B. So we get C there. Need F, connect that. G and D. Okay. Bring our light over, turn the circuit on. Again, nothing shows on display. Take the light away, number 5 begins to show. Cover up our photoresistor, gets nice and bright. Let some light back in, gets dimmer, bring our 6-foot lamp back over, and it goes out. Okay. So that's 471. 472, we're going to display number 6. So we need A, C, D, E, so we need to put 1 on there, F, and G. So, just put it back over. That circuit on, nothing displays, take it away. Number 6 begins to show. Cover up our photoresistor, it's now nice and bright. Once again, we let light back in, gets a little dimmer because we're decreasing that resistance there. Put a 6-foot lamp over, and it goes completely out. And this 6-foot lamp's getting hot to hold. So that is 472. So 473, we're now going to display number 7. So we connect points A, B, and C. Take all these away. Take it lamp over. Kind of stick it. Nothing happens. Take our light away. Number 7 begins lighting. Cover up our photoresistor, it gets it nice and bright, let the light back in, it gets a little dimmer, bring plenty of light in, and it goes completely out. So that's 473. So 474, we're now going to display 8. So we need to connect A, B, C, D, E, F, and G. D, E, F, and G. Bring our light back over. Turn the circuit on. Number 8 doesn't display. Start letting that light in and decreasing the resistance allows us to see our number 8. Cover up our photoresistor. And it's showing number 8. It's interesting though. Oh, okay, that's why. Connection is a little weak there. I was wondering why I was trying to show 0. So there's our 8. Bring it right back over, and it goes completely out. So that's project 474. So 475 wants to display number 9. So we got A, B, don't need C, D, don't need E, F, G, and C. I guess they don't follow alphabetical order after all. A, B, D, F, G, and C. I don't know why they couldn't have gotten A, B, C, D, F, G, but whatever. So, bring our light over, turn on the circuit. Again, number 9 doesn't display, we take it away, starts to show up. Cover up our photoresistor, it gets it nice and bright. Let some light in, starts getting dim. Bring our 6-volt lamp over, and it goes completely out. So that's 475, so now 476 is the number 0. So we connect A, B, C, D, E, and F. Take G away. Like that. A, B, C, D, E, F. Okay. Bring our light over. Turn on the circuit. Node 0. Let some light in on that photoresistor. The 0 begins to display. Cover up our photoresistor. Glows nice and bright. Let some light in. It gets a little dim. Bring some more light in. And it goes completely out. So, that is project 476. And now we're going to move on to project 477, which is the variable oscillator. So here we are with project 477 through 484. So we got the variable oscillator. There it is in the book, and here it is on the board. So we got ourselves another oscillating circuit here to produce a tone. So we got our transformer outputting to our speaker, using our C1 and C2 capacitors for coupling, along with our R5 100,000 ohm resistor feeding our variable resistor, which is connected to the base of our NPN transistor, which helps again produce the oscillation effect by turning the NPN transistor on and off, which then creates our signal for our transformer, and then it outputs to our speaker. So we start off with our variable resistor all the way to the bottom here. We turn it on, and we get a low consistent tone generated out of our speaker there. And of course, as we change the resistance on our variable resistor, we can make the frequency higher so that the tone is at a higher hertz than you would say down here or down here. So that's project 477. Now project 478, we're going to take our whistle chip and we're going to connect it across our NPN transistor. So now we get output from both the speaker and the whistle chip, because now we hear it through the whistle chip as well. So that's project 478. Now project 479 has the whistle chip connected across our C2 capacitor. So I can take it off there and put it here. And now it's added a little bit of capacitance in parallel with our C2 capacitor there, and by doing that, the tone of the circuit is lower that it's producing. So that's project 479. So project 480 now has us connect the whistle chip across our C1 capacitor. So now we're going to put it in parallel with the capacitor C1. And that decreases the tone of the circuit even further, so a lower frequency. So that's project 480. So with project 481, we're going to take our 100,000 ohm resistor out and replace it with our photoresistor and control the circuit's resistance that way. So move that to the side here. Take this out. Find that our photoresistor is, stick it in there. Get this part connected up. And now by using the photoresistor, we can vary the resistance in two ways, both with our variable resistor here and with how much light goes into our photoresistor. So turn the circuit on. So already we get a different tone out based on the ambient light that we got going in there. And of course, waving my hand, putting a shadow over it already changes that. And of course, by decreasing the resistance there, it of course affects the base of our transistor there and slows down the oscillation of the circuit considerably. Now, of course, if we were to take something like the 6-volt lamp here, plug this in, and of course decrease the resistance putting light in. I meant to say increasing the resistance when I was covering it up like this. If we allow less resistance there, then we can actually speed up, or I should say increase the frequency of the circuit there. Now again, it sounds like it's stopping, but actually the circuit is oscillating in such a way that we can't hear it. So that's how project number 481 works, and now we're going to move on to project 482. In that, we're just going to take the speaker out and use our whistle chip without the speaker involved. So we'll disconnect that, and we'll use the whistle chip in the same positions that we had before. So first we're going to connect it across our NPN transistor. Also going to take our photoresistor out and put our 100,000 ohm resistor back in its place. So we have a fixed amount here. We turn our circuit on. And now we just have our audio coming out of our whistle chip. But as you see, the whistle chip behaves differently than what the circuit did when we had the speaker there instead. So now let's move it in parallel with capacitor C2, see what happens there. And we really can't move our variable resistor past the middle position here. Otherwise it will cut out on us. Again, it also could be that the circuit is simply oscillating in a manner that we can't hear. Alright, now let's put this in parallel with capacitor C1. See how that sounds. So that is project number 482. Now project 483, going to use our speaker again, but this time we're going to take our 10 microfarad capacitor and we're going to put it in parallel with our C1 capacitor, positive pointing up. And then when we turn on the circuit, we've added so much capacitance to that now that the circuit is just basically oscillating so slowly that it's pulsing. And again, by using our variable resistor, we can adjust that rate. So that is how project number 483 works. Now for project 484, we're going to change that for even more capacitance. So we're going to take the 10 microfarad out, and we're going to put the 100 microfarad in its place. Although, let's see, there it is. So we take the 100 microfarad, and just like before, now we're adding 10 times the capacitance to the circuit because we had our 10 microfarad there, and now we got 100. So turn it on. And now the circuit oscillates even slower than before, because again, 10 times the capacitance there. So that's number project 484. So now we're going to look at project 485, which is the fixed current path. So here we have project number 485, the fixed current path. There it is in the book, and here it is on the board. And this is a pretty simple circuit. All it has is a 3-volt source, our slide switch, 10,000 ohm resistor, and our meter set to the low setting. So we turn on our circuit. Meter pretty much deflects all the way over to 10 because it tells us that, hey, there's 10 milliamps in the circuit here. We got a 3-volt source, we got a 10,000 ohm resistor here, so we get about 10 milliamps of overall current going through the circuit. And the resistor helps limit the amount of current going through the circuit. If this was any lower, well, the meter would deflect over more. But there's not too much to project 485. That's how that one works. So now we're going to move on to project 486, which is the simple illumination meter. So here we are with project number 486, the simple illumination meter. Here it is in the book, and here it is on the board. And before I talk about the circuit, I have to confess I did it again. Here's that new 3-volt lamp I just showed in the previous video, blown to smithereens. Because I was using the 6-volt for this. I already had the leads here attached to that, and as you see from there, I hooked it up to the 6-volt. Poof, blew that 3-volt lamp out of the water. So got to send off for another one. Luckily, the remaining projects in the book here for the 500 series does not include the 3-volt lamp in them, nor does it need the 6-volt, so I don't have to worry about being held back not having another one of those available. So with this project, we have our photoresistor and adjustable resistor here now controlling the current in our circuit. So when we have our variable resistor set all the way to the left, and we turn it on, we get about 5 milliamps of current going through the circuit, because this setup allows the photoresistor to be very sensitive to the amount of light coming into it to affect our circuit. So as you see, putting my hand there briefly makes it deflect almost all the way to 0, because the photoresistor has a lot of effect on the circuit. Now, of course, if I bring the 6-volt lamp over and put the light in there, well, now it goes even more to the right, almost full deflection. Now, if we bring the variable resistor all the way to the right, well, now the circuit is less sensitive to light there, because now we only got maybe about a milliamp going through it. And bringing our light over, it doesn't really increase it that much, because again, it doesn't affect it that much having so much resistance on the circuit there with it set to the right. So that is how project number 486 works. So now we're going to look at project 487, which is LED voltage drop. So here we have project number 487, the LED voltage drop. There it is in the book, and here it is on the board. Again, another pretty simple circuit. We have our meter set to the low setting, being limited by our 10,000 ohm resistor, which is going through our red LED. And then we have our press switch here to help bypass it, so we can illustrate how LED voltage drop works. So we turn on the circuit, and we get to about 6 milliamps of current according to the meter there, and our LED is dimly lit there. Now if we press our press switch to bypass it, meter deflects pretty much almost to 10 milliamps, because the voltage across our R4 resistor there increases, because we no longer have the voltage drop that's being induced by our red LED. Bring the red LED back into the circuit, we get a voltage drop, so we get less current through the overall circuit. And again, the same thing can be done with our green LED as well to see the difference there. So that's how project 487 works, and now we're going to look at project 488, which is the open-closed door indicator. Here we have project 488, the open-closed door indicator. There it is in the book, and here it is on the board. So here we've got our 7-segment LED, which is being limited by our 100 ohm resistor. We're running 6 volts here. Got our slide switch, our NPN transistor, which is doing some control of the 7-segment LED, which has got our 10,000 ohm resistor running through it, and then its base is being controlled via our photoresistor. So A, F, E, and D are constantly on their 7-segment LED, and then B and C are turned on and off via our NPN transistor there. So when we turn the circuit on, we have the letter O being displayed on our 7-segment LED, displaying that, okay, something is open because the photoresistor is seeing light there, allowing the NPN transistor to be turned on. Now if we cover it up, we take current away from the transistor, turning off segments B and C. So now it displays the letter C to say, oh hey, the door is closed, because it's not seeing any light. Once it sees light again, it lights up those 2 segments on the right there, because our NPN transistor turns on, and shows that again when we cover up our photoresistor, displays the letter C, because again we turned our NPN transistor off. So that's how project 488 works, and that concludes this set of Snap Circuits videos.